So what we're now going to do is see some transformations among the different type of variations of binary tree. So in this course we saw a binary tree could be a binary search tree, it could be a heap, and if it's a heap it could be a max heap or a min heap. So what we are going to do is how to transform or change from one format of a binary tree to another. So we could transform a max heap to a min heap, or a min heap to a max heap, max or min heap to okay, one second, I have a question. In the next DQ process, 8 would have been the parent node of 7. Okay, let me check. Okay, so what would happen if you DQ this Q? 9 comes out, so the last index is going to be 5, sorry, index 4, right? So that's the last index. So you will make 5 as a temporary root node data. So after you DQ this, 9 goes out and you make the data of the last index. The last index is 4 and 5 is now the temporary data for the root node. So now we have to reheapify. So 5 compared with 7 and 8. So that means 5 is actually less than both the child node data. So we'll swap 5, the larger of the two child nodes. So 8 will go to the root node index, 5 comes here. So, and that's the leaf node position. So you don't have to check further down. So the next DQ process will result in 8 becoming the root, then 7 and 5, and then for 7 you'll have 1 as the child node data. So this index is no longer going to be part of the heap. So that's the answer. Let me check if the student got it. Okay. Alright, so let's now do this. So here I have given in this slide, it's like a master slide, the rule for doing all these transformations. So you can use it for reference purpose, but now we are going to do each of these transformations and again explain the rule here. So the first few, like a max heap to a min heap or min heap to max heap, are going to be straightforward based on what we have seen so far, but let us just go through that again. So think about it. So you're given a max heap. So this is a max heap and you want to convert that to a min heap. So a min heap means for every internal node, the data of that internal node should be less than or equal to both the child node data. So you have to work around, move around the elements here such that the root node actually has the smallest value among these elements. So, and then further down and so on. So how we accomplish that? So we could reheapify starting from the last internal node. Okay, and if you do that and to check for the min heap property at every internal node, we will eventually transform the max heap to a min heap. So that's what we are going to do. So the last internal node in this max heap is index 2. So now starting from that last internal node, check if the internal node satisfies the min heap property, because that's what we want to accomplish. We want to transform this max heap to a min heap. So make sure now the min heap property is satisfied at every internal node starting from the last internal node. So the last internal node at index 2. So now check if it satisfies the min heap property. So in this case compare 23 with its child node data, which is 18. So obviously it was a max heap to begin with, right? So it won't satisfy the min heap property. So we have to do the swapping. So swap 18 with 23. So 18 comes here, 23 goes down. Now this is a leaf node position, so you don't have to check further down. So after this swap, you will have 18 as the data here and 23 comes here. Now the next internal node index is index 1. So reheapify at this index. So again compare the data at that index with the data of the two child nodes to make sure it satisfies a min heap property. So 22 is in this case less than greater than both 13 and 14. So that's not satisfying the min heap property. So swap. Now you see here this index has two child nodes at index 3 and 4. So you have to find and make sure what you want to do at index 1. You want to make it a min heap, satisfy the min heap property. So in order to do that, we have to pick the smaller of the two child node data. So you have to be careful here. We want to make it a min heap. So you have to pick the smaller of the two child node data, which is in this case 13. So you have to swap the index here with the smaller of the two child node data. So 22 comes down, 13 goes up. Now again, this index 3 is a leaf node position, so you don't have to check further down. So 13 is the data here at index 1. So now we have to reheapify at index 0. So you're going to have 27 compared with 13 and 18. 27 is greater than both the child nodes. We have to swap with what is smaller of the two child node data. So 13 and 18, 13 is smaller. So 13 goes up and 27 comes down here. Now this is an internal node position and the min heap property may not be satisfied further down. So you have to check further down. So 27 compared with 22 and 14, 27 is actually greater than both. So you have to swap with smaller of the two child node data. So 27 comes down and 14 goes up. So this is a leaf node position, so you don't have to check further down. So after we go through this process, this is the final min heap. So 13 is here, 14 has moved here, and 27 further down. Okay, so you can check. This is now min heap. Every internal node is less than or equal to both its child nodes. 13 less than 14 and 18, 14 less than 22 and 27, 18 less than 23. Okay, so we'll do one more example. So this is a given max heap. So you want to now transform this to a min heap. So the way we do that is start from the last internal node, which is index 4, and check if it is satisfying the min heap property. So in this case, index 4 is the last internal node, 6 compared with 3. 6 is actually greater than 3, so you want to make this index data to be less than its child index. So you swap. So because of that, 6 comes further down and 3 goes up. So this is a leaf node position to which you have moved the data 6. So that's not going to do anything further down. So we leave with that. And then check the next internal node, which is index 3 with both the child nodes. 5 is kind of equal to 5 but not less than 4. So you have to swap with the smaller of the two child node data, so which is 4. So 4 goes up, 5 comes down, and that's a leaf node position, so you don't check further down. And then you reheapify at the next index internal node, which is index 2. So 9 compared to 1 and 7, 9 is greater than both, so swap with the smaller of the two child node data. So 1 is the smaller one, so 1 goes up, 9 comes down, and that's a leaf node position, so you don't have to check further down. Now at index 1 is the next internal node, so compare 8 with 3 and 4. 8 is greater than both, so swap with the smaller. So 8 comes down, 3 goes up. Now this is an internal node position, so compare further down. So 8 compared with 6, 8 is greater than 6. We want to make sure each internal node position is a min heap. So that's what we actually want to accomplish. Each internal node position should be satisfying the min heap property. So 8 compared with 6, 8 is greater than 6, so do a swap. So 8 comes down, this is a leaf node, no further down, and 6 goes here. So that's the min heap now. Now the last iteration, index 0, compare 10 with 3 and 1. 10 is greater than both, so swap with the smaller of the two child node data. So 1 goes up, 10 goes down. That's the internal node position, so you have to check further down. So 10 compared with 7 and 9, 10 is greater than both. So swap with the smaller of the two child node data. So 7 goes up, 10 comes down. So after we do that, we'll have the min heap property satisfied. So the entire binary tree is now a min heap, and you can always cross check. At every internal node, the data will be less than or equal to the child node data. So this is how you can change from a max heap to a min heap. Now the same approach could be used to, so I don't show it here, but I can leave it for you to try. So what we saw just now is how to change a max heap to a min heap. Now the same approach can be done to transform a min heap to a max heap. So how we do that? Again, start from the last internal node. So let us see here. So this is the this is the min heap. So the last internal node at index 2. So now we want to make sure, we want to transform this to a max heap. So at every internal node, the max heap property should be satisfied. So compared with the child node data, in this case 18 compared with 23, 18 is less than 23. So you want to make this index a max heap index. So swap. So 18 comes down and 23 goes above. So you accomplish this as the, where is that? So 23 will be here, 18 will be here. Then again reheapify at the previous internal node index and so on. So you can change from a max heap to a min heap as well as from min heap to a max heap. So each, for both, you have to just make sure what you want to accomplish and change the internal index data correspondingly, okay, or by doing the swapping with the child node data. Okay, so let us now see the other transformation, which is given a min heap or a max heap, we want to now transform that to a binary search tree, and we did this in the beginning of this module and also the earlier module. Why? Because any thing, either a min heap or a max heap, is essentially a binary tree. So we know how to transform a binary tree to a binary search tree by preserving the structure and just rearranging the data. So the way we do that is we do an in-order traversal of the binary tree. So in this case, let us say you are given a max heap and you want to transform this max heap to a binary search tree. So do an in-order traversal of the given max heap. And as you do the in-order traversal, write down both the index as well as the data that you traverse for the nodes. So the in-order traversal, the rule is what? The left, root, right. So that means start with the root, but don't list the root right away. Go to the left subtree, and don't list the root right away. Go to its left subtree, and then go to its left subtree. So that means the first node that will be listed is index 7, and the corresponding data is 5. Then go to the root node. So that is index 3, and the corresponding data is 5. Then go to the right child, which is index 8, and data 4. So done with the left subtree, go to the root of this, which is index 1, and the data is 8. Now go to the right subtree. For the right subtree, the root is 4. So go to its left subtree, which is index 9, and the corresponding data 3. So now print the root, which is index 4, and the data 6. So now we are done with the left subtree. Go to the root, which is index 0, and the corresponding data 10. Now go to the right subtree, don't print the root right away, go to the left subtree, which is index 5, the corresponding data is 1. Then print the root, which is 2, the data is 9, and then print the right subtree, which is index 6, and the data is 7. So that's the first step. So given a max heap, you do in-order traversal of the max heap, or even the same thing for a min heap. So treat it as a binary tree. Do that, and then once you get the in-order traversal list for both the index and the data, keep the index sequence as it is, just sort the data. So when you sort the data, this is the sorted order of the data, and now all we are going to do is just superimpose. So at index 7, you are going to have data 1. So whatever the data at index 7, you are going to replace that with data 1. At index 3, we are going to have data 3. At index 8, you are going to have data 4. So whatever the data, just superimpose. Some data may stay the same, but some will get changed. So at index 1, you are going to have 5. So at index 1, you are having 5. At index 9, you are having 5. Okay. So after we do the superimpose, what we get is going to be a binary search tree. And you can again cross-check whether the property of a binary search tree is satisfied. The property is for every internal node, the data should be greater than or equal to its left child and less than or equal to its right child. That's for a binary search tree. So 7 greater than 5 but less than 9. 5 greater than 3 but less than 6. 9 greater than 8 but less than 10, and so on. So for every internal node, the data should be greater than or equal to its left child data and less than or equal to its right child data for a binary search tree. Now we can do that similarly for a min heap. As I said, treat it just as a binary tree and do the in-order traversal. So if you do an in-order traversal of this min heap, again you are going to go all the way further down and list 7 index and then the corresponding data 5 and then 3 and the corresponding data 4 and then 8 and 5. Then done with the left subtree, list the root which is 1 and the data 3. Then go to the right subtree, list the left child of the root which is 9 and the data 8 and then the root of the right subtree 4 and the data 6 and so on. So just again sort the data and superimpose. So at index 7 you're going to have 1, at index 3 you're going to have 3 and index 8 you're going to have 4 and index 1 you're going to have 5 and so on. So this way you can transform a min heap to a binary search tree. So for both a max heap or a min heap, to change that to a binary search tree, simply do the in-order traversal of both the data as well as the index and sort the data and superimpose the data with the index corresponding index. So let us see now the other two transformation. So what we are going to do now is how to transform a binary search tree to a max heap or a min heap. So that's the thing we are going to see now. Alright, so we'll see first from a binary search tree to a min heap. So this is the rule. To transform a binary search tree to a min heap, we have to do two traversals of the binary search tree. Do an in-order traversal of the binary search tree based on just the data and list only the data. So do an in-order traversal of the binary search tree and list only the data of the nodes. So if you do that, in-order traversal again is left, root, right. So go to the left subtree, which is this, go to the left, which is this. So list the data there, which is 13. And then go to the root node, which is the data is 14. And then go to the right subtree, the data is 18. So done with this left subtree, go to the root node, the data is 22. Then go to the right subtree, don't print the root data, go to the left child, which is data is 23. And the root data for this is 27. So this is the in-order based listing of just the data values of this binary search tree. And then what you do is do a pre-order listing of the nodes, the node index values of this binary search tree. So now what you do is a pre-order traversal of the binary search tree and list only the index of the nodes you to traverse. So when you do a pre-order is root left right. So list the root right away 0. Then go to the left subtree, list the root right away, which is 1. Then go to the left subtree, list the root right away, which is 3. So then with the left subtree, go to the root, which is what? So this is pre-order, so root left right. So we did the root, done with the left, then go to the right, which is going to be index 4. Then done with the left subtree, done with the root, go to the right subtree. The right subtree lists the root right away, which is 2. Then go to the left subtree, which is 5. So this is a pre-order listing of the nodes. So once you have the pre-order listing of the nodes and the in-order listing of the data, just superimpose them. So at index 0, we are going to have 13. At index 1, we are going to have 14. At index 3, we are going to have 18. At index 4, 22 and so on. So once we do that superimpose, what we end up with is a min heap. So again, you can cross check the property for a min heap. Every internal node, the data should be less than or equal to both the child node data. So 13 less than both 14 and 23, 14 less than both 18 and 22, 23 less than 27 and so on. Okay, so we'll see one more. Okay, so this is for a binary search tree to a min heap. So the rule is do an in-order traversal of the binary search tree and list the data, and do a pre-order traversal of the binary search tree and list the node index and just superimpose them. So let us now do the other one, the binary search tree to a max heap. So for that, again, do the in-order traversal for the data, but instead of pre-order traversal, because you do pre-order traversal to convert to a min heap, now to convert to a max heap, do a post-order traversal. So we saw the in-order traversal already. So let us see the post-order traversal. So post-order, the rule is left, right, root. So start with the root, don't list the index of the root right away, go to the left subtree. Now for the left subtree, the root is 1, don't list it right away, go to its left subtree. So the index is 3, so there's no left subtree further down. So if there's further down, you would have gone there, but there's no left child, no right child, so then list the root, which is 3. So done with the left child or the left subtree, go to the right subtree of this root, which is this. So list 4. So done with the left and right subtrees, now list the root, which is index 1. So done with the left subtree, don't go to the root right away, go to its right subtree. So the right subtree is this. Then don't list the root right away, go to the left child. We don't have anything further down, so list 5. And then done with the left subtree, there's no right subtree. If there was a right subtree, you would have gone there. So now list the root, which is index 2. And then done with the right subtree, list the root, which is index 0. So this is the way you do post-order traversal of a binary tree. So once you get the post-order traversal and of the node index and the in-order traversal of the data, just superimpose. So at node 3, you are going to have 13. At node 4, you are going to have 14. At node 1, you are going to have 18. At node 5, you are going to have 22. And then node 2, you are going to have 23. Node 0, you are going to have 27. And you can cross check whether the resulting binary tree is a max heap. The internal node data should be greater than or equal to both the child node data for every internal node. Okay, so this is how you will transform a binary search tree to a max heap by doing post-order traversal. Now I have one more example for you to practice, binary search tree to min heap. So the way we do that is do an in-order traversal of the tree and write only the data in the in-order traversal. So this is a binary search tree, so you can cross-check also. When you do an in-order traversal of a binary search tree, you're going to have the data in a sorted order. So that's what has happened in the previous examples too. When you do an in-order traversal of a binary search tree, you will list the data in a sorted order. So you can cross-check whether you're doing right. So how you do an in-order traversal of this? In order means left, root, right. So go start with the root, but don't list the root data, go to its left and then go to the left and then go to the left. So 1 is first thing to be listed. Then list the root node data, which is 3. Then list the right child data, which is 4. Done with this left subtree, list the root node data, which is 5. Now go to the right subtree, don't list the root data, go to the left subtree, list this 5 and then list the root data, which is 6. Now done with this left subtree, list the root data, which is 7. Then go to the right subtree, don't list 9, go to its left child data, so 8, followed by the root 9, followed by 10. So this is the in-order traversal for the data. Now this is to a min heap. So the rule for min heap is to do a pre-order traversal of the binary search tree and list the node index. So pre-order is root, left, right. So start with the root, list it right away, so 0. Then go to the left subtree, list the root right away, 1. Then go to the left subtree, which is 3, list the root. Then go to the left, 7. So listed all the left subtree, then go to the right subtree, so which is going to be 8. So done with this left subtree, already listed the root. So root, left subtree, then go to the right subtree. So list the root right away, so 4. Then list the left subtree, left child, which is index 9. So done with the root, done with the left subtree, go to the right subtree. List the root right away, so index 2. Then go to the right, left child, so index 5. So done with the root, done with the left, now list the right index, which is 6. So this is a pre-order listing of the node index values, and just superimpose, you will, with the index with the data, you will get a min heap. Okay, so I have another example for binary search to max heap, so I'll let you to practice this, and we'll just finish this example next time. We are out of time, and we'll move on to the next module, which is graph. Okay, so I posted a take-home exam 3. You can start working on it. It will cover whatever you have seen so far, so it's time to get started on that. All right, so we'll stop with this.